Am I audible?
Yes, sir.
So this class we will study about the instruction set which is extensively used to perform the bit manipulations in embedded systems. If somebody asks what is the difference between a microprocessor and a microcontroller, one of the difference which we can always tell is the microcontrollers support bit manipulation by providing a lot of instructions suitable for that. So extensive bit manipulation is performed in microcontroller based systems, unlike in case of a microprocessor based systems. If you ask the question why, in microprocessor based systems, you do not worry about the memory too much because it's a huge memory is available for you. You don't mind allocating a bytes for storing certain information, that is variables. You don't go for bit variables. Minimum you start with what? Integer, like that you start. But whereas in case of an embedded systems, the memory is the important because memory is not outside the chip, memory is inside the chip. Whenever the memory comes inside the chip, the way of programming is different. When you put memory outside the chip, the way of programming is different because you don't care for the memory. When you put it inside, you care for the memory. So whenever you put inside, the memory is simple, memory is very small, then what do you think in the programming? Every bit counts there, not the every byte, every bit counts. So I'll use to represent everything outside my project, that is whatever the census data and everything, whatever I want to represent in my program, I'll see that can a bit is sufficient to represent the data. So if I have to represent certain variable, first what comes to my mind? Oh, can I represent that information, that variable by a single bit? If it is possible, I'll represent a single bit. So like that, if I'm able in many of the sensor, for example, you have a certain device, whether the device is on and off, that's all you want to store the information. If the device is on, you perform certain logics. If the device is off, you perform certain logics. Or you want to control certain devices. Those devices are just on and off. Whenever certain devices, certain sensors gives the data which is on and off, basically you have to represent by one bit is good enough. One means on, zero means off. So a lot of information related to your project, related to the data which is coming from outside world, we represent in terms of bits. So whenever we represent a lot of information in terms of bits, so microcontroller is required to support that bit manipulation. So what are the bit manipulations we generally is going to do it? For example, I have a memory is available. If my memory is, if this is my memory, so memory is nothing but what? Representation of bits. Let's say D31 is the first bit, then D30 the second bit, it continues, and then say let's say D1 and the D0. These are the bits are available. Now, what are the bit manipulations I'm able to do it? So let's say this memory location represents a lot of information. It's not a one information like a age or a sex or the name of a person. No, it's not a one information. I'm using this 32 bits to represent lots of information. Maybe 5 related to 5 sensors. I may be embedding, encoding the information to this one. So whenever you encode a lot of information to this one, every bit is a count for you. You have to perform manipulation. What is the manipulation required? Let's say I am interested to clear D1, which represents some sensor, which represents some device, and then I have to clear D30 bits. That means that I am interested in this number in the memory location to clear what number, what bits, D1 bit and D3 bit. I want to make it 0, so that whenever I make it 0, what will happen? Corresponding to devices which I'm using, which I'm controlling outside the microcontroller, will be switched off. So like this, that's the number one operation is what we require. So we want to clear the selected bits. We want to clear the selected bits. This is one form of bit manipulation. So similarly, opposite of this is what for example, I'm interested to make D29 bit and then some bit here somewhere. So let's say D18. I want to make D29 bit and D18 bit as 1. That means that I have to set that devices which corresponding to the devices outside world. So sometimes we require to set, or it's nothing but what? It's basically switch on. Switch on D29 and D18 bits. This is required. Am I audible?
Yes, sir.
Yes, sir.
So the other, what is another operation we require is sometimes you do not worry about whether it is a on or off. You want to just reverse the operation. So it was working the machine. You want to just make it opposite of that operation for some time. So we just, for example, if you are using an LED, you want to just toggle the LED. So what I'll do is, that is when I say toggle, I say complement. So complement the, let's say D31 and D0 bit. So like this. So these are the three basic operations which forms what is called as bit manipulation. Clearing the selected bits, setting the selected bits, and complementing the selected bits. So these are extensively is called as a bit manipulation. So how do you perform this bit manipulation? How do you perform this bit manipulation in the memory? So now we will see that what are the instructions are provided to perform these bit manipulations. So bit manipulations in memory. So all the microcontrollers, including the microprocessors, provide these three instructions for the bit manipulations. So they are called as logical instructions. They are called as logical instructions. So what are the logical instructions they provide? They provide AND, so they provide OR, and they provide XOR. So these are the commonly available instructions which are provided in almost all the microcontroller based systems. Now, so we will study these instructions now and how we can use these instructions to perform these bit manipulations. Whenever we perform a bit manipulation, we use a term called as mask bytes, mask words. We use a term called as mask. So what is that? We will see that. So a mask is nothing but a 32-bit number, which I'll be preparing it based on what type of operation I'm going to perform. If I'm going to perform the clearing the selected bits, I'll prepare a mask which is useful for me to clear the bits. That's why I can call as a mask for a particular operation. So for example, if I want to clear the selected bits, the operation which I'm going to use is always AND operation. If I want to set a corresponding bits, I'll be using an operation called as OR operation. I'll be using it. If I'm going to perform an operation which is going to complement the bits, I'm going to use an operation called XOR operation. So whenever I want to perform an AND operation, what do I require? So I have a given number which is being taken from a memory. You have a given number. I want to say I want to clear a particular bits of the number which is stored in a memory. Then what I do is, so I will prepare another 32-bit number. There in the selected positions, I will make 1 or 0, depends upon what operation I'm going to prepare it. If it's an AND, the selected bits will be 1. If it's an OR, selected bits will be, in case of an AND, the selected bits will be 0. In case of OR, the selected bits will be 1. In case of XOR, selected bits will be 1. We will see that. So I'll prepare the second word based on the operation I'm going to perform. The second word which I'm going to prepare, which is going to apply on the number which has been given from the memory, it's called as a mask word. It's called as a mask word. So I'll be using a word called as a mask word. So this mask word is applied on the given 32-bit number. So to perform bit manipulation. So now we will see that all the three examples, how it's going to be performed now. So now we will perform all those operations now. So we will take the first question now. So write a program. Write a first question. What we do is now. So we will do. Okay. So I will take the first program now. First operation we will understand. So my question is now. Write a program to clear the D0, D11 bits of a given 32-bit number. So I have taken one number from the memory. Instead of storing in the memory and then bringing it, I'm just loading the number directly. You assume that this is a number taken from a memory. Assume that. What is the number I have taken? 32-bit number. This is the number I have taken, F00. So I have splitted the number. F means 111, then 000, then FA is there, 111, A is there, that is 1010, then 0F. So this is the binary equivalent of the number whatever I split. This number I have noted the bit position. D0 is the first bit, 7th bit, 8th, 11th, 16th bit, 31 bit. I have given the notations for the bits. Now my question is what? I have to clear D0 and D11 bits. That means that I should not modify any other bits here. I have to modify only what bit? D0 bit. What? D0 bit I have to modify. What is that I have to modify? Since you have taken a number from memory, this D0 bit can be 0 or 1. We don't know. Depends upon the what value is there in the memory. So irrespective of 1 or 0, it is there at this position. I have to make it what? I have to clear this bit. So I have to clear this bit irrespective if it's 1 or 0. Next is what bit? D11 bit. So this is the D11 bit. So this is a 7, 8, 9, 10, 11. This is the 11th bit. So now what is this bit? Irrespective of this bit is 1 or 0, I have to clear this bit. I have to make it 0. Now, whenever the selected bits, you have to make it 0 only 11th bit and the D0 bit. You should not disturb the other bits. So for that, we have to prepare one mask pattern. So this mask pattern I'm going to apply on this number so that only those bits should become 0. So what type of mask it called? We call it the AND mask. Because AND is an operation, I can use it to clear selected bits. In case of an AND mask preparation, what is the rule is there? Whichever the bit you want to make it 0, that corresponding bit in the mask you have to make it 0. See, for example, look at here. I have to clear D0 and D11 bits. So write a program to clear D0 and D11 bits. D0. So I'm clearing other bits. So instead I'll just change the bits number here. So I want to clear D31. So I will clear a D31 so that I have prepared what? 0 here. I have prepared a 0 here. Because why I have prepared a 0? I have to correspondingly D31 bit I have cleared it. I want to clear it. I have taken it. Next, I have taken another bit called 11th bit. So D31 and then so D11 I have taken it. D11. So now what has happened? D11 bit is this bit. The corresponding bit I have made it 0. So now all the bits first what you write? You write 1, 1, 1, 1, 1. Then whichever the bits you want to clear, those corresponding bits you make it 0. And only those bits you make it 0. All other bits you make it 1. Now my pattern is ready. So this pattern now convert into hexadecimal. So it is nothing but 7. So 7 I have written it. Again this is 7. So I have written 7. All other FFF. So this mask, this is called as a mask pattern. So it's called as what? AND mask I have prepared it. Now I will apply this number onto this number. When I apply into this number to this number, what is an operation supposed to perform? And operation I have to perform. So and operation is supposed to perform. So and yes, R0, R1. R1 is a mask, R0 is actual number we have prepared. Are you able to see Keel screen? Hello?
Yes, sir.
Yes, sir.
Okay. So now I compile my program. I'll compile my program. Now I'll see that whether the required value I'll get or not. Now I'll do till the stage. I'll got the first number R0, that is FF0, A0F. This is the number I loaded. The second number, which is nothing but the mask pattern 7 FFFF, 7 is there. Now I'll find out the answer before I just run the instruction. Now you have to AND this number, the first number, and you AND the second number. What is the result I'm going to get? I'll copy the same number from here to here is my answer. Only thing is the D31 bit has become 0 and the D11 bit has become 0. All other thing, my answer is what? It is similar to the first number what is there in the memory, except for that is a D31 bit, 11 bit I made 0. Now what is my answer? So 0, 1, 1 is 7, 0, 0, 0. Here my answer is changed to then 0F. So this is my answer. So same as what is there in the memory, 2 bits I made 0. This is the answer I supposed to get it. 7, 0, 0, 0F to 0F I supposed to get it. Now R0, some other value is there. What is there in the memory is there. Now I apply. Now I'll run my program. Now see that what is an answer you supposed to got it. 7, 0, 0, 0, F to 0F. That is same as whatever we calculated. So that means that my answer, correct now. So it doesn't match with the the requirement. What is the requirement? You are supposed to clear the selected bits. So this is a fundamental rule we use in low-level programming. Even high-level programming also, we can use the same concept to clear the selected bits of a number. So we have understood now the first program, how we can able to clear the selected bits of a number. That is one bit manipulation we did. Now I'll take the another example, the second one. So I'll take the second one, second case. Now I'll select it. Now second case is, my question is, now I know how to clear it. Now what I have to do, I have to set it. I have to set the D7, D4, D0 bit. Now I have taken the same number in the memory, whatever the previous example. I split all the bits now. Now I'll go to the first bit, D0 bit. See, look at the D0 bit. Now this D0 bit, I have to set it. Whether it is 1 already or 0, I am not interested. I have to just make this bit is equal to 1, irrespective of whether it's 1 or 0. Now what is the mask pattern? I have to use the mask pattern which I'm going to use now is called Arm mask. Whichever the bit you want to set, the corresponding bit you make it 1. All the bits you make it 0. That is, first I'll write everything 0. Then I'll write 1 in the position where I want the setting. So this bit I made it 0, 1 because D0 bit is required. So then this is 27th bit, D27 bit, I made it 1. So these are the two bits I'm interested. So D0 and then the D4. D4 also I made it 1. So these three bits I made it 1, 1, 1, 1. Now what is my mask byte or mask word? 0, 8, 0, 0, 0, 1 and the 1. So my mask word is ready. Now what I'll do, load the mask word into the R1 register, apply the OR operation. Instead of logical and in the case of bit and in the previous case, I'm doing a OR operation. So R0, R1. Now we'll see the result. What is the result? Is expected result. So the result is nothing but the same thing. Whatever the number is there in the memory, I'll copy the same number. Only thing I'll change wherever the bit which is supposed to set, I'll make it 1, irrespective of whatever the value there. See, D0, I made it 1 in the result. That is changed here. Then D4, it was 0 here. Now it has become 1. So now D27, it was 0 here. Now it has become a 1. My result is what? So this is my result. So convert into hexadecimal, F800 FA1F. Now I'll compile my program and see that whether do I get a same result. So okay. So now I load both the numbers. Both the numbers is readily available here. Now look at the result. That is this, whatever the number you have in the R0 should change to this value. Then my requirement will be satisfied. Now look at that. F800 FA1F. That means my result is as per my expectation. So now I have understood how to set the required bits of a number stored in a memory. Now we will go to the last operation. So what is the last operation? So as you know that already, one of the very frequently used things is a toggling. So we will do the toggling now. Toggling means nothing but what? Complementing the bits. How do we do that complementing bits? Again, I have taken the same number. I have not changed the number. Only thing, my requirement is different now. So I've taken the last bit D31 and the first bit D0. I want to complement it. Let's say this is my number. This is my number. Last bit D0 bit. If it is 1, I have to make it 0. If it is 0, I have to make it 1. In this case, it is a 1. I have to produce as what? 0. I have to complement it. I'll go to the 31 bit. So 31 bit is what? It's a 1 is there. I have to make it 0. If it is 0 was there, I would have supposed to make it 1. Now I have to prepare the mask word. Now, whenever you want to complement any bit, you cannot use the AND. You cannot use the OR. Only operation possible is an XOR operation. Let's understand the XOR operation. So how does the XOR operation will work? We know that in the case of an XOR, if both the inputs, if you take a single gate, if both are 0, output is what? 0 always. If both are same, that is 1, 1, then output is what? 0. If one is 0, other is 1, your output is 1. Other case, 1 and then 0, output is equal to 1. If you look at any XOR operation, basically is what? You are applying one XOR gate for every bit. Now, how many XOR gates are there internally to perform this operation? 32 XOR gates are there. I'm just taken one example. So see that in case of an XOR, if both the inputs are same, then output will be what? 0. If inputs are different, if the one is 0, other is a 1, the output is what? 1. Now let's consider this one, D0. Now, if I want to complement this bit D0, what should I do it? If I XOR this number with a 1, then what will happen? Since both are 1, 1, output becomes what? 0 by chance. the D0 bit is 1 in the memory, D0 bit is 0 in the memory. Then what I'll do, since I'm XORing always with the 1, 0 and the 1, see both are what? So both are in this case different is 0 and 1. Output will become what? The 1. So that means that it is possible to invert or complement any bit in the memory when you XOR with the 1. Because why? If it's already 1, 1, 1, it becomes 0. That means that you are inverting the 1 to 0. If it is 0, you are XORing with the 1. So when both our inputs are not same, in case of XOR, you are getting a 1. So that means that XORing any number with a corresponding mask word such that whichever the bit you want to invert, corresponding bit you have to write 1. Now in this case, for example, I want to invert or complement D0. So now what will happen? So I'll make everything right 0, 0 to start with. Only the bits which is I'm interested. Now D0 I'm interested. So D0 I'm interested. I'll write as what? In the mask word 1. Now D31 I have to complement. Write in the mask word 1. Now my mask word is ready. So what is the mask word? 80001. Now, so I will apply my logic. What is the logic? Perform this number XOR with the mask word. So XOR mask word. Then what do you get? So this bit 1 is there. It becomes complemented. All other bits becomes, it will not change. 1 XOR 0, 1, 1 XOR 0, it will not change. When you XOR with the 0, whatever the value is there, you will get the same thing. See, look at the last one. 1 XOR 1, well, sorry, 1, 1 XOR, it becomes 0. Here also it was 1, 1 XOR 0. So that means that, so wherever you're interested, only those bits are being complemented. You should always remember that by chance I have taken here 0 here. Instead of that, let's say my number in the memory is 0. My number in the memory. Then what is my answer? Look at that. 0, 1. It becomes what? The last bit becomes 1. It is nothing but what? Complement of 0. It becomes a 1. Here also 0 XOR 1. It becomes what? 1. So that means that whether the number bit here in the required memory location is 0 or 1, when you XOR with the 1, it becomes invert. So I'll just revert back the number. Okay. So now we will compile this program, see that whether do we get this answer or not. So now I'll execute these two instructions. F0, I got the same number. The answer is now is supposed to be there in the R0. Now I'll execute that instruction. Look at that. 700 FADE, 700 FADE, FA0E. That is the same answer. I got it. So this is how you can able to produce the required bit manipulations in case of a embedded systems. Even in a high-level language also, you can follow the same concept. So 3 operations we were able to do it. So one is AND operation, OR and XOR. If the question is given, that is sometimes what will happen. So they will give a question which involves multiple operations. They say that write a program to complement the question. Let's say to complement D0 bit, set D31 bit, set D31 bit, set D31 bit. So then clear D2 bit. Let's say question is like this. So what I have to do? I have to perform all the operations one by one. So now I'll do one by one operation now here. So now let's say LDR R0. Now I assume that R0 contains a memory location number. So I'll declare a num. Some number I'll be given TCD. So and F A C D A 8 9, some number I have taken it. Say take a number. So I load the number into memory location. So LDR, let's say into the R0 itself. So I'll get from a R0 memory location. I'll go to it. Let's see. So now I have got a number from memory location. That is num. This number into the R0 register. Now I have to perform all these operations. My question is what? I have to do all these operations. The first, I'll take the first clear operation. So I have to clear the D2 bit, D2 bit. So then what I'll do, I prepare now AND mask. Let R1. So I have to prepare an AND mask. So what I'll do is I have to make it, in case of AND mask, all 0 0 0 0. Only the bits which you are interested, sorry, all 1 1 1. The bits which you are want to make it 0, you have to make it 0. So 1 1 1 1 1 1 1. Now here 1 D2 bit is required, D0 D1 D2. So 0 and then 1 1. So the first bit is D0, then D1, this is D2 bit. So I want to clear the D2 bit in the given number. So now what is my pattern? So my pattern will be LDR on equals. So F. So then F. So 8 9 AB, it is a B. So I'll just take this number, I'll put it here. Now my first number is ready, that is the first mask is ready. So now similarly I have to prepare the second mask. Let's say second mask is always setting, I'll take always setting LDR. Let's say R2 equals second. So which bit I have to set? I have to set the 31 bit. So whenever I set the 31 bit, it's very clear that whichever the bit you want to set, you have to make it 1. Remaining bits you have to make it 0 0. So it continues like this. So now R2 is equal to, I'll write in hexadecimal format. So 0x, so 8 0 0 0 0 0 0. So I've got the, now second mask is ready. Now the third mask is, I have to prepare the third mask. LDR R3 equals, so what is the bit we have to complement? So I have to complement the D0 bit. So since whichever the bit I want to complement, I have to make it 1. So that means that all are 0 0 0 except the last bit. So last bit I'll make it 1. So now this will be 0 x 0 0 0 0 1. So now all my masks are ready. That is AND mask, OR mask, and a XOR mask words are ready. Now I have to perform the operation. It is very simple for you now to do it. And first apply the AND mask, that is R1 contains. So next OR mask you apply R0, and then what is called R2. Then you want to perform XOR mask R0, R3. So now if you compile this program, so take this number, split into binary pattern, see that the required 3 operations would have been performed. You can just verify this. I'll just show you the result. You can verify that operation. Now I performed the 3 numbers, I've loaded it. Now the first AND R0 R1. Now what will happen? D2 bit becomes 0. So you can see that in the whatever the result, D2 bit becomes 0. Now the second one. Now in the R, that is D31 becomes set. You can clearly see that it's become NF there. So in the complement, then what will happen? XOR. So the whatever the D, that is D0 bit, it has been complemented. So you can split this number into binary pattern, see that all these operations has been happened. So this is how you can able to perform in a single program multiple operations. These are commonly required bit manipulations in the industry. So we have understood now how to do a bit manipulations. There is a one operation explicitly provided. Here, for example, so let's say I'll remove this code. Okay. Now there is always a requirement of clearing the bits. Now if I want to clear the bits, what is the way it's available for me to clear any of the bits is I have to go to I have to prepare I'm audible.
Yes, sir.
Okay. So if I want to do clearing the bits, the only methods available for me is what? You to prepare an AND mask and apply that AND mask to this number, whatever there. So in preparing an AND mask, little confusion is there. That is, whichever the bit you want to make it 0, you have to make it 0. Other bits you have to make it 1. So just think that if there is any facility is there, whichever the bits I want to make it clear, yes or no, I don't require to perform AND operation, everything. It's I have to remember AND operation, I have to make it 0, I have to make other bits 1. It's little confusion. Is it a way to make it easy? What is an easy? Whichever the bits I want to make it clear, I have to just say 1. So I'm interested to make it 0. I'm not interested. I'm interested to make this bit is equal to 0. Correct now. So now give single instruction. So give a single instruction. Take this number in one register, apply this number in other register, perform that instruction. This looks better than the AND operation. So for that, to support that, they have provided one instruction. It's a beautiful instruction. So it is called as a bit clear, BIC clear instruction, bit clear. How does it perform basically? So we will understand the bit clear instruction now. So bit clear instruction, basically, it is nothing but BIC, bit clear instruction. Now, where is a number? As usual, number can be there in any of the register. Let's say LDR is equal to R0 is equal to some number, I have it, bit clear. So let's say it is an 0x. So some number I'll take it, 0x. So F I'll take it. So or I'll take 8. I'll take an 8. Or let's say F I'll take it. Then 0, 0, 0. Then 0, 0. F I'll take it. So I have taken this number. So this number, now what is the result I supposed to get it? I want to, let's say, clear the following bits. What are the bits I want to clear? Let's say D31 bit I want to clear is, D30 bit I have to clear it, and the D0 bit I have to clear it. So this also I have to clear it. Let's say these are the bits I want to clear it. Now, so what I'll do, I'll take another register now, LDR R1. I'll take another register equals. I'll write what are the bits I required, so that I'll prepare very easily. Now 1, 1, 0, 0. I'm not interested. Only the bits which I want to make it clear. Now look at this. So now I prepared a pattern. So what is this pattern is? I am making the bits which I am interested to clear just 1, 1 wherever there, and D0 is equal to 1. I made it. Now what is my pattern? So 0, 0, X. So this is nothing but 1, 1 is 8, 9, A, B, C. That is C, C. Then 0, 0, 0, 0, 0, and this is a 1. So I made it. It's ready now. So C, one more 0, I think 0. Okay. Now it's ready. Now bit clear. What are the bit you have to apply? Bit clear R0, R1. I applied it. That's all. See, look, it's very so simple. Whichever the bit you want to make it clear, you will load into another register, apply in this number, bit clear. Just the name says. Now we will see that. How does it work? So I compiled program. So what is my answer? What is my answer? So in my answer, whatever the number I have taken, this is the number I have taken. So let's write the number I have taken. So the number is 1, 1, 1, 1, 1. All others are 0, 0, 0, 0, 0, 0, 0, 0, 0, and then 1, 1, 1. So what is my result? Only those bits has been cleared. So my result, I'll write the result before I run the program. So this becomes 0 because you're clearing that 0, 0, and then remaining things 1, 1, and 0, 0, 0. So then 1, 1, 1, 0. So the hexadecimal value of that, hexadecimal value of this is equal to, so this is 3, 0, 0, 0, 0, 0, and this is V. That means that this is the number given to me. The requirement was clear D31, D30, and the D0 bits. So I just indicated through another register and I cleared those bits. And after clearing those two bits, these two bits and the D0 bit, this is the number I got it. So let's compile the program. So now run the first instruction. Now I got F00F and the C001 is a number I got into that. Now I want to see that what is the result in the R0. I'll finish execution. See that 3000. I got the result. See that it looks so simple to clear the required bits because clearing the bits is very extensively used. Instead of using AND operation, this operation can be used. But what is actually bit clear will do inside? Basically, the bit clear is nothing but so operand 1 and operation, and then what? Not of, this is operand 1, this is operand 1, not of operand 2. Basically, they have performed. That's all. Operand 2. So what is a bit clear instruction? Bit clear instruction is nothing but you're taking on operand 1. You, instead of performing directly and I am doing what operation? Not of operand 2. So that what will happen? Wherever 1 1 0 is there, 1 1 is there, it becomes 0, other becomes 1 1. It is basically performing an AND, but it is easier for you to prepare. So the instruction itself performs the not of operand 2 and then performs the AND operation. So bit clear is implemented using the AND operation and a not operation that used it. So these are the how bit clear will be helpful to clear the bits. So now we have seen the 4 bit manipulation instructions supported by the ARM microcontroller. So what are those? And XOR, OR, and the bit clear. One thing you have to remember is whenever you perform arithmetic operation like an addition, subtraction, we are very much interested in all the flags. What are the flags we are interested? We are interested in carry, we are interested in 0, we are interested in overflow, we are interested in sign, because after performing arithmetic operation or a comparison operation, we extensively branch based on these conditions. But when I perform a logical operations, do you think that all the flags are important? Just think, I'm performing an AND operation between 2 numbers. Anytime do you are interested in carry flag? Anytime you are interested in overflow flag? Anytime you are interested in the sign flag? No. Whenever we perform a logical operations, we are generally interested in only what is a 0, whether the answer is 0 or not. That's all. So we are not interested in the whether my answer is carry is generated or not. That is not the meaning of performing a logical operation like a bit manipulation operations. So that is why in case of ARM microcontroller also, overflow flag and the carry flag are not affected by these logical operations. Only in case of carry flag will change if you are going to introduce a shift operation in one of the operand. If you want to shift a number and then apply the logical operation, then whatever the shifting you perform, that will be set into the carry flag appropriately based on the shift operation you're going to perform. Because we know that whenever we perform any of the shift operations or rotate operations, carry flag is getting affected. The last shift out or the last bit which you rotate will go into the carry flag. So if you don't perform a shift operation, carry is not going to affect it and the overflow is not going to affect it. The sign and 0 flag will get affected, but we generally look at what? Only the 0 flag. So whenever we do logical operations, I am interested to test what? Only whether my answer is 0 or not. So otherwise it's not required. So can you tell me one condition where you are performing an operation and check whether the answer is 0 or not? This is one of the beautiful requirement for bit manipulations. What is that I want to do it? For example, I'll come to an example here. Now I'll remove sorry, entry I put it there otherwise. Okay, so let's say I remove this number. So now now my requirement is the 3 bit manipulations we have understood now. That is a clearing, setting, and complementing. There's one more 4th requirement in the bit manipulations extensively used in the industry. Let's say D31, 32 bits of a memory location are used to represent 32 different sensor data which is being connected to the microcontroller. Different sensors are available. Or in a given sensor, different flags are represented by these 32 bits. Different states of the sensor are represented by 32 bits. Let's say now let's say I am interested in the D1. So I want to check whether the D1 condition, D1 bit is what, 1 or 0. If it is a 1, I want to take a certain decision. If it is 0, I have to take another decision. Am I audible?
Yes, sir.
Okay. So what is the 4th requirement of a bit manipulation? I am interested to test a particular bit of a memory location, and they test whether it's a 1 or 0. Basically, all the bits corresponding to what? One sensor. Now, how many sensors are connected? Let's say 32 sensors has been represented by this one word. Now, I'm writing a program. In between the program somewhere, I want to find out if this sensor is on I want to do certain action. If the sensor is off, I want to do certain action. Then how do we do it? How do you do it? I don't want to change the number. I don't want to change my number. In the previous three cases, what will happen? You're basically changing the number. In the sense, what if you perform an AND operation, you change the number. If you perform OR operation, you change the original number. In case of an XOR also, you change the original number. Now, I am not interested to manipulate this number. I am just want to check whether the sensor 1, which is represented with the D1 bit, is on or off. For that, testing like this, you can always use it if you're on and off like that. What is the one method we can do it? One method is whichever the bit you are interested, retain that bit. All the bits you make it 0. One method. So this method, there's one method, that is make all the bits 0, except the bit which you are interested, make it what? 1, remaining bit 0. So this is a mask we prepare it. So what I'm doing it, I'm ANDing this number. So since I may modify this number, I'll keep this number probably in other register if I'm interested with the number, since I may modify the number. So what I'll do now, I want to test only this bit. How do I test it? Only this bit. Now prepare a mask. In that mask, make all the bits which you are not interested in testing 0, 0. Only the bit which you want to test it, you make it 1, corresponding bit 1, all of the 0. Now, what is the pattern I'll get? Now this I'll get the pattern. This is 0, 0, 0, 0, then 0, 0, 0, 2. This is the pattern I got it. Now, this pattern, mask pattern, I'll perform what operation? I'll load the number. Let's say I load the number R0, R0 with some number 0x, FFFF, 89AF, some number I have taken it. This is the number I loaded from the web. Now I want to test a particular bit. So I prepared a mask pattern. What is my mask pattern? 0x, 0, 0, 0, then 0, 0, 0, 2. I prepared a mask pattern. Now I have to perform certain operation such that only the bit which you are in the sensor which you are interested should reflect my answer. Other things should not reflect. So what I do is I will perform an operation. The operation is called as AND operation. I will perform. Why I am performing an AND operation is whenever I perform AND operation on the number whose D2 bit I am interested to test. So I'll perform an AND operation. Now A and D, R0 with the R1. Now, what is the result I'll get it? Now the result, it depends upon what? Look at here. The result depends upon what? The results depends upon all the bits. These bits are zeros. All these bits are 0. There is no doubt, and because I'm performing an AND operation with zeros. Now this bit, whatever you're going to get it, yes or no, this is very important bit, because why? The next bit is also 0. Only this bit. Now the result depends upon what bit? Depends upon the D1 bit of an actual number. If the D1 bit of an actual number is 0, this bit becomes what? 0. So remember here properly. If the D1 bit is 0, then this bit becomes 0 by chance. If the D1 bit is 1, then your result bit, then the result in the result bit, this bit becomes what? 1. So that means that the D1 bit in the answer depends upon what is the value is there in your number which you want to test it. For example, if the sensor is 1, the answer is what? 1 in the resultant bit. If the sensor is 0, the answer is also what? 0. That means that if you look at the overall value of this number, since the all other bits is already 0, except the D1 bit which you are interested, since the whole number becomes 0 if the D1 becomes 0. Listen to me carefully. The whole number becomes 0 if the D1 bit is 0. Because why? You are already all other bits become 0. And if this D1 is 0, the whole number becomes what? 0. That is 0 flag is set. If the whole number becomes a non-zero number, I am not telling you what a particular number. I am telling you it's a non-zero number. It's not a 0. If the D1 bit of a, that is if sensor is 1. If the sensor is 1, the whole bit becomes a non-zero. That means that the result I am interested to produce only two states. Result is a what? Either 0 or non-zero I am producing. So then whenever I perform, I will use what is called S now here. Why I am using S? Because I'm interested to perform this operation only to test a particular bit is set or not, particular sensor is on or off. I'm not interested to manipulate now in the previous 3 cases. Now after this, I'll perform the impression. So then branch equal, so on. So I'll do something operation on, that is branch equal sensor. So let's say every equal means what? Zero flag is set. That means that off. So I'll do certain operations here. So what is the operation I'll do? Sensor off. I write some logics here. I'll write some logic here. Now not equal, I'll write some logics here. So that means that if the total answer is 0, that means that what? The sensor is what? Off. That sensor is 0. So sensor produces 0. That sensor is off. I'll come to here. I'll do certain operation what is required. So if it is the one is 1, that is sensor is on, then what will happen? It is 0 flag is not set. I'll do some operations here. Only thing is you have to branch here. So branch skip or something you have to write to here. The end of the program you have to write like this, skip here. So this is the only thing you have to do. So look at here. Now the whole of this program is extensively used in embedded system to test the particular bits of a memory location or to test the sensors which are represented by a particular bits of memory location, which is on and off. It's on, I have to do certain operations. So these are one of the methods people use to test a particular bits on and off. Now, so now I'll do a little modification for this one. So what is this program? So this program, so this is a program for testing the required bits of a memory which represents sensors, which represents the sensors. So now I'll do certain modification for this program. Okay, now I want to do the same operation, but again performing an AND operation. What is the disadvantage with an AND operation? Can you tell me here? Anybody can able to just tell what is the disadvantage in AND operation here? If I'm performing AND operation like that, can somebody tell me? Can somebody tell me?
So you have to check only for one bit, but you are doing it for all the 32 bits in the number.
So that's one by one I can do it. Anyway, you have to do like that only, no? So if you're taking if by chance, if you're interested in 2 sensor testing at a time and all those things, I'll be using the 2 bits, clearing and all those things. Otherwise, individually one by one only I have to do it. So that's not a disadvantage. Yes or no? There's no other way. So what is the disadvantage of using an AND operation here? What is an advantage? Yeah, somebody is telling correct answer. Tell me.
So the value gets changed of R naught. So we're not just testing it, but we're changing the value also.
Yeah, it's very important. So in this case, what is happening here? So you are losing the value what is there in the R0 register, because what you are manipulating also for the purpose of testing it. To avoid this one, like a comparison operation, whenever you do a comparison operation instead of subtraction, it is similar to subtraction, but your destination operand will not be modified, but the requirement of flags affecting will be done. So same thing is given here, what is called as test instruction, TST instruction is being given here. So what is the test instruction will do it? Test instruction basically performs an AND operation, but do not affect the destination register. So that is why it's called as a pseudo AND operation. It's also called a pseudo AND operation. So what I have to do? I have to replace AND S. I have to replace AND S here by test. That's all I have to do. So this test instruction is nothing but pseudo AND instruction. Everything, whatever I did, everything is same thing. Wherever I use AND operation, I just use a test. So what is the purpose of test? Test is used to test a particular bit is 0 or 1. For that part, test is used to test a particular sensor is on or off, which is represented by a memory location. This is the meaning of a test instruction. So we have covered AND, OR, XOR, bit clear, and the test. So there is one more last operation is there, which is also pseudo operation. So which is used so for checking the equality of a number. How do you test whether 2 numbers are equal or not? Many times it's required. 2 variables are represented by the 2 register. I want to check whether they're equal or not. So one method you can do a comparison operation. So we know that XOR operation is used to test whether equal or not. How we will use an XOR operation? XOR operation is extensively used for test for whether they are equal or not. Let's say you have a one number in a one register, one number in another register. Let's say if you XOR the same number, let's say you have a one number in a register, I'll copy the same number into another register. Say I have a number, Control C. So I will copy this into another register. Now, if I perform the XOR operations of these two numbers which are same, what is your result? Since all the bits are same in both the cases, in both the places, the result is also 0. That means that whenever the two numbers are equal, if you perform the XOR operation, the result is always 0. That is 0 flag is set. So similarly, whenever they are not equal, the 0 flag will not be set, because at least one or two bits will be what? It becomes a 1. So test equal, TEQ, is used to test the equality of the two registers. So if you want to test any two registers whether equal or not, one is a comparison, you can able to do it, or subtraction, you can able to do it. So apart from that, you can do what is called pseudo XOR operation. TEQ is nothing but pseudo XOR operation. So TEQ performs the XOR operation of R0 and R1, set the 0 flag if both are equal. If they are not equal, 0 flag will not be set. Based on that, you can take a condition. So you can use T equal. So you can use test operations. So for implementing your logics in your programs. So this completes all our instructions which are used for a bit manipulation. So what are the pseudo instruction we studied? Compare, T equal, test are the pseudo instruction. There is one more reverse comparison is there. Instead of R1 minus R2, you can do R2 minus R1. That is also pseudo operation. So basically there are 4 instructions available performing pseudo operations. They are generally used to perform what is called as they are used to perform branching. They'll be used to affect the flags, and based on that we'll perform the branching. So this completes today's discussion of that. We will have an extra class today at 4:30. So I will not 4:30. So I'll just let you know. I'll just message you one more class, because I'm not sure whether we'll get an extra one more class before